let's talk about continuity. Oh, and I always do this. Every single, so the thing I'm complaining to myself that I always do is I take notes about what you all have said in the reflections, like what you would like to see and talk about, and then I promptly leave those notes in my office every time. I mean, I pretty much remember what I wrote down, but like, it just feels like the dumbest thing. Like I could actually bring those notes with me, maybe someday. Really, James? Every time, every time, every time. Seems like every time I do this. Oh well. Yep, they're not here. Okay, that's just fine. It just feels like could be a little bit smarter about that. All right, so let's talk about continuity. And what I would say about continuity is there are essentially, when we're trying to see whether or not a function is continuous at a particular point, we check three things. So to see if f of x is continuous at x equal to a, we check three things. One, does f of a exist? Two, does the limit as x approaches a of f of x exist? And three, most importantly, are they equal to each other? Meaning, does the limit as x approaches a of f of x equal f of a? One sec. If all three things are true, then the function is continuous at that point. If any one of them is not true, the function is discontinuous at that point. Go ahead, question?
Yeah, for the limit of x, what does that say after?
Exist. Yeah, sorry, my penmanship always a challenge here. A of f of x. I will also point out that if you're looking in a textbook and they're talking about the definition of continuity, they usually only write this last thing. So for a function to be continuous at the point A, all that needs to be true is for the limit as x approaches a of f of x has to equal f of a. Because if this is true, it also had to be true that the limit existed and the function existed. So when you're saying this is true, it also implies these two things. But when you're trying to show it for a question, it's usually easier to break it down into these three steps. So that's why we usually write it that way. Let's look at some examples. Promptly close my binder here. Okay. Sure, we'll look at that example. So let's say we have the following. So I'm going to phrase this in a typical way. Where is the function f of x equal to x squared plus 1 when x is less than 0? Cosine of x when x is bigger than or equal to 0 and less than or equal to pi. And sure, 3x plus 1 when x is bigger than pi. Where is this function continuous? So to answer this question, we first need to say a few things about the continuity of functions in general. So someone asked me, and I think it was a really good question. So we're going to take a quick kind of aside here. Most, and this is, I know it's a vague term, most functions are continuous on their domains. So let me be a little bit more explicit about this. So here is a not exhaustive list of functions that are continuous where they are defined. First and foremost, polynomials. are continuous everywhere because they're defined everywhere. So an example of this would be, say, the polynomial f of x equal to 2x cubed plus 5x plus 1. Or the polynomial g of x equal to 7. Yeah, 7's a polynomial. It's just a really boring one. It's a 0th degree polynomial. Or, I don't know, h of x equal to 3x to the 1000th power. As long as the powers are non-negative integer powers of x. So you can't have a fractional power. You can't have an irrational power. You can't have a negative power because then you start having discontinuities. Okay, what else is continuous on its domain? Rational functions. Rational functions are just polynomials divided by polynomials. And I should kind of box these here. So an example of this would be f of x equal to 3x squared plus 5x plus 2 over x minus 1 squared. This function is not continuous everywhere because it's not defined everywhere. But this function is continuous everywhere except for x equal to positive 1. So this function is continuous on its domain, which is everything from negative infinity to 1, union 1 to infinity. So when I say something like, or when anyone says something like, this function is continuous on its domain or where it's defined, that's what they mean. Meaning where it's not defined, it's not continuous, but everywhere else is continuous. And I should have picked something that was a little easier to draw. So I'm gonna give you one more example because I know how to, because this one, I can't draw this very nicely right off the bat. But if I look at say something like, for another example here, g of x equal to, say, sure, let's make it nice and fun, James, 4 over x minus 3. This function is continuous everywhere except for 3. So it's continuous on the interval from negative infinity to positive 3, union positive 3 to infinity, excluding 3. And here's what that function looks like. Got a vertical asymptote at x equal to 3. And again, it's not going to be a perfect graph, but it's going to look vaguely like, let's see, something kind of like this. So any value of x besides 3, it's continuous. Like if we look over here, you know, say 4, yeah, the function is continuous around that point, right? It's defined. The limit from the left and the right are the same. They're both equal to whatever the function value is, and they're both, so the limit's equal to the function value. So as long as the function is defined, it's typically continuous there. There are some exceptions. That's why I said most, not all. I'll give you a couple more items on my list, and then we'll get back to the question we started with. So, polynomials, rational functions. The 2 other things, the 3 other things I will list are, sure, trig functions. Sine and cosine are continuous. Oh, sorry, you can't see that. Apologies. Trig functions. Sine of x and cosine of x are continuous everywhere because they're defined everywhere. And the other 4 quotient functions, tangent of x, cotangent of x, secant of x, and cosecant of x, are continuous on their domains. For example, and I'm not going to draw this because it just doesn't ever look nice when I draw it. But if we look at, I don't know if we make this bigger for a second here, sorry. So we look at the tangent function. It looks like that. It's got a bunch of vertical asymptotes. It's got a vertical asymptote every odd multiple of pi over 2. So if you graph like x equal to pi over 2, there's a vertical asymptote, or x equal to 3 pi over 2. There's another vertical asymptote. So what we would say here is this function is continuous everywhere except for all those values where you have a vertical asymptote, except for everywhere where it's not defined. It's not defined there because tangent is sine of x over cosine of x, and cosine of x is equal to 0 at pi over 2, and 3 pi over 2, and 5 pi over 2, 7 pi over 2, and so on and so on and so on. Writing the domain for tangent is kind of a pain, but it's doable. You could say, for example, that tangent of x is continuous because it's defined on, here's kind of the easier way to write it. We just say, well, it's union pi over 2 to 3 pi over 2 union, and then we just do some dot dot dots like that. Everything like that. So you're just excluding every odd multiple of pi over 2. Okay, last two things in my list. Exponential functions. So things like e to the x, 2 to the x, 3 to the x minus 5. And those are typically continuous everywhere because they're defined everywhere. And the last thing on my list, not that this list is exhaustive because it isn't, are logarithmic functions. So things like f of x equal to the natural log of x, or g of x equal to the log base 2 of x minus 8, and so on and so on and so on. These ones are continuous on their domains. So this first one would be continuous on the interval from 0 to infinity, because that's where the logarithmic function is defined. The second one would be continuous on the interval from 8 to infinity, because that's where that one happens to be defined. So it's kind of a lot to say, but I'll just go back and say again, most functions, or I should say most normal-ish functions, and I'll say more about that in a second, are continuous on their domains. The main exception being piecewise functions. Piecewise functions are almost always not continuous on their entire domain, because there usually are examples of functions that have discontinuities in interesting ways. So back to the example that I started with, which I should have maybe not written out on this other piece of paper, but well, such is life. Yeah, back to this previous example. So where is this function continuous? Well, here's what I point out. Each of the pieces, in fact, let me just write this function again. So for f of x equal to this piecewise function, x squared plus 1 when x is less than 0, cosine of x when x is between 0 and pi, and 3x plus 1 when x is larger than pi. Get rid of that. So each of the individual pieces are functions that are continuous on their own domains. X squared plus 1 is a polynomial. It's continuous everywhere. Cosine of x is a trig function that's defined everywhere. It's continuous everywhere. 3x plus 1 is also a polynomial. It's a straight line. It's continuous everywhere. So all these functions are continuous everywhere. They're defined in their own right. So the only places where we're concerned about discontinuity is where we change from one piece to the next piece, because maybe they're not matching up. So when we ask, where is this function continuous? What we're really kind of focusing in on is, where is it potentially discontinuous? So we're going to look at the two places for this piecewise function where we change from one piece of the function to the next piece of the function. Specifically at x equal to 0, because that's where we change from x squared plus 1 to cosine, and at x equal to pi, where we change from cosine to 3x plus 1. So let's focus in on x equal to 0 first. So when I'm trying to determine continuity at a particular point, I'm going to start by doing the three things. First, I'm going to look at, does f of 0 exist? Well, if I try to look at f of 0, I'm going to plug 0 into which piece of my piecewise function? The top piece, the middle piece, or the bottom piece? the middle piece, because that's where x is equal to 0. So f of 0 is going to be cosine of 0. And what's cosine of 0? It's sine of 0. I heard a 0 anyway. Sine of 0 is 0. Cosine of 0 is indeed 1. Great. Second part, the limit. So we want to find the limit as x approaches 0 of f of x. Often, although not always, this will involve looking at each of the one-sided limits, because typically for these piecewise functions, the function is defined to be a different thing on the left side of 0 and the right side of 0, or whatever point you're looking at. So we're going to look at both sides. Look at the limit as x approaches 0 from the left of f of x, which is going to be the limit as x approaches 0 from the left of, well, if I'm left of 0, I am less than 0, and I have to use the piece of the function where x is less than 0. I'm using the x squared plus 1 piece. And then I evaluate the limit in the easiest way possible. I plug in 0. I get 0 squared plus 1, which is 1. And do the same thing for the other side. I look at the limit as x approaches 0 from the right of f of x. That's going to be the limit as x approaches 0 from the right of, well, the piece where x is just bigger than 0 is cosine of x. We evaluate the limit also by just plugging in 0. We get cosine of 0, which is also 1. And those match. So that means that the limit as x approaches 0 of f of x is indeed equal to 1. Now, that's not enough. People like to stop there and say, oh, the limit exists, we're done. You have to say one more thing. You have to say that the limit value is equal to the function value. So part 3, I usually sum up by saying either it is or it isn't. I'm going to say f of x is continuous at x equal to 0 because the limit as x approaches 0 of f of x is equal to the same thing that f of 0 is equal to. Cool. Let's look at the other place of concern. Pi. Now I wish I did that. Sorry. So cover that up. I know it's terrible. So let's look at x equal to pi. Same deal. We're going to do the same 3 things. The first thing we're going to do is, what's f of pi going to be? Well, again, I'm plugging into the middle piece because that's where x is defined to be equal to pi. So f of pi is going to be cosine of pi, which is -1. And then part 2, the limit. So the limit as x approaches pi of f of x, we're again going to look at both sides of that limit. So we're going to look at the limit as x approaches pi from the left of f of x. In this case, the limit as x approaches pi from the left, we're going to have to use the piece where x is less than pi, so we're going to have to use the cosine piece. Now, I will point out, if you're using the same piece that you just used to evaluate the function, the limit ends up typically being the same value. So I know I'm just going to plug in pi here. I'm going to get cosine of pi, which is again equal to -1. On the other side, the limit as x approaches pi from the right of f of x, we're going to get the limit as x approaches pi from the right of 3x plus 1, because that's where x is defined to be larger than pi. And if you plug in pi here, you're going to get 3 times pi plus 1. And I don't know exactly what that is, but I know for sure it's not equal to -1, right? It's like 10 point something. And that's enough to say that this function is discontinuous. The limit doesn't exist. The limit as x approaches pi of f of x does not exist. And if one of these 3 things fails, we fail to be continuous. So that means f of x is not continuous at x equal to pi. And now to fully answer the question, where is f of x continuous? We look at all the places of discontinuity. We exclude those, and then everything else is in. So the only place where this function was discontinuous was at x equal to pi. So everything else is valid. So we're going to say that our function f of x is continuous on the interval from -infinity to pi union pi to infinity. a couple language things here. If you asked me, is this function a continuous function? My answer would be no. Because if it's discontinuous in at least one place, it is discontinuous. So that language, so even though most functions we look at are continuous almost everywhere, if they're discontinuous in at least one spot, we usually call them a discontinuous function. All right, let's look at one more example and then we will move along. Let's look at the following thing. Let's say we have f of x equal to x squared minus 25 over x minus 5 when x is not equal to 5, and 17 when x is equal to 5. I will point out again, both of these functions are continuous on their own respective domains. 17 is a polynomial. Again, it's kind of a boring one, right? It's just a horizontal line, but it's certainly continuous everywhere. Certainly continuous at x equal to 5. X squared minus 25 over x minus 5 is a rational function, and it's continuous everywhere that it's defined. And it's defined everywhere except for 5, so it's continuous everywhere because the only place it wouldn't be defined would be at 5. So both of these functions are continuous where they're defined. We just have to see if they're matching up at the one place where we switch from like one thing to the other thing. I will also point out another way you could write this, if you found it more convenient, although I don't find it more convenient, would be to write it as it's x squared minus 25 over x minus 5 when x is less than 5. It's 17 when x is equal to 5. And it's the same x squared minus 25 over x minus 5 when x is greater than 5. We don't need to write it that way, but I just want to point out that on the left side of 5 and the right side of 5, the function is defined to be this x squared minus 25 over x minus 5. Okay, so the only place we're concerned about continuity is it continuous at x equal to 5? Everywhere else, we already know it's continuous. So we check the usual things. We're going to look at f of 5. We're going to look at the limit as x approaches 5. So f of 5 should be super easy to answer. You should be able to look at that page and be like, oh yeah, I know what f of 5 is without doing any work whatsoever. Because we've already been told that if you plug in 5 for x, you get 17 for f of 5. Okay, the limit is a little more interesting. Here, we do not need to look at both sides of the limit because on the left side and the right side, the function is the same thing. So you don't want to do two one-sided limits here. You just want to do one double-sided limit since it's the same function on the left and the right of 5. So if I look at the limit as x approaches 5, it's going to be the limit as x approaches 5 of x squared minus 25 over x minus 5. If we plug in 5, we're going to get a 0 over 0. So we're going to have to do some algebra before we can actually evaluate this limit. So we're going to factor. Again, knowing that plugging in 5 got me a 0 on top means I know that x minus 5 has to be a factor on top. I know the top is going to factor as x minus 5 times x plus 5. X minus 5. I can cancel those x minus 5s. And then I get the limit's going to be the limit as x approaches 5 of x plus 5, which is going to be 5 plus 5, which is 10. And here's where people make a very common mistake. They're like, oh, the limit exists. Great, it's continuous. It's not continuous, right? The limit is 10. The function is 17. Those aren't the same. So this function is discontinuous at x equal to 5 because the function value and the limit value don't match up. So we would say that f of x is discontinuous or not continuous, whichever word you prefer to use, at x equal to 5 because, and I do think if it were up to me, I would always require people to say the reason why it's discontinuous. Because sometimes it's discontinuous because the function doesn't exist. Sometimes it's discontinuous because the limit doesn't exist. And sometimes it's discontinuous because they're not matching up. I think it's always a good idea to write down in what way it's discontinuous, although you might not be required to do that. So here it's discontinuous at x equal to 5 because f of 5 does not equal the limit as x approaches 5 of f of x. Because the right side of that is 10 and the left side of that is 17. Those are not the same. And then after you do all this, you have to remind yourself what the question was really asking. The question was really asking, where is this continuous? Actually, I guess I didn't say that explicitly, but that's usually the question. So we can then go back and say, okay, great. F of x is continuous everywhere else. So it's continuous on the interval from -infinity to 5. Almost everywhere. And we still call it discontinuous. Okay, there's one more thing I want to say here. Oh yeah, I know. Often with a question like this, you get asked how you could redefine the function at 5 so that the function would be continuous. So what would we have to change 17 into so this function would be continuous at 5? 10, right? And usually if you've done all this work, it's relatively obvious. Like, oh yeah, if we change this to 10 to make the whole thing continuous everywhere, make f of x continuous everywhere. And I could talk about continuity for another hour, but we got other things to say, so we're gonna. All right. Still kind of on the topic of continuity, we have the intermediate value theorem, which is certainly heavily related to the topic of continuity. So we have the intermediate value theorem, which almost everybody abbreviates intermediate value theorem, also known as the IVT. So the idea with the intermediate value theorem is really that if a function is continuous on some interval, and you have some lower y value and some higher y value, you get every y value in between. That's the whole gist, really. Let me draw a picture though. So let's say we had something like this. We have some, so let's say we have some a value here, and we know that f of a happens to be, I don't know, let's say 60. Just to make up some numbers. And over here, we have some b value, and f of b is something large like, I don't know, 6,000. And the function is continuous on this interval from a to b. So maybe it looks something like this. Down a little bit, and then up, and then oh, like that. There's my continuous function from a to b. And maybe it does something else after this. I don't really care. Like that. So here's what the intermediate value theorem says. Between a and b, if f of x is continuous, then you get every y value between f of a and f of b. So I could ask the question, is there, wow, can I spell? Not usually. Is there a number between a and b? We usually call it c, such that, wow, sorry, the writing is just, I can't even like help myself, sorry. Such that f of c is equal to 3,000. Let's see. 3,000 is about right there-ish. And if we go over, we can say, well, if I look over here at 3,000, oh yeah, that point right there, if I look at the corresponding x coordinate, that would be the c value such that f of c was equal to 3,000. And that should be true, or I should say, the intermediate value theorem guarantees that that is true for any y value, in this example, between 60 and 6,000. So here are the words of the intermediate value theorem. So if f of x is continuous on some closed interval from a to b, and we let n be any number between f of a and f of b, then there must be a number C between A and B so that f of C is equal to n. There exists at least one number. There might be more. We're going to call it C between A and B such that f of C is equal to whatever number you get. So that's only going to be true if the function is continuous and that y number, that capital N we picked, is between f of A and f of B. Okay, let's talk about a couple of examples. Well, I should say, are there questions about what the theorem is saying? So let me point out, there might be more than one. For example, if I picked a number here, the number pretend is like 2,500. If we look here and you go across this way, oh, look, it looks like there's like maybe two different spots where you would have had C value between A and B. The theorem just says there has to be at least one. There could be more. We don't care. The theorem just says there's got to be at least one. So typically, what we use a theorem for is to show that equations have solutions. Not to find the solutions, but show that equations have solutions. Let me give you two examples. So, and I like the map. So let's look at this example. Show that x cubed plus x squared plus x equal to 10 has at least one solution between x equal to 1 and x equal to 2. Okay. So whenever you have a problem like this where you're asked to show there's a solution but not actually find the solution, because I don't know what the solution is going to be here, and I'm not going to find it. But what you want to do is you almost always want to make it a show that some other equation equal to 0 has a solution. So first things first, reframe the question. Reframe as showing x cubed plus x squared plus x minus 10 equal to 0 has a solution. Still in the same interval. In the interval from 1 to 2. And then whatever is on the left side that isn't 0, we're going to call this here, call this f of x, or whatever letter you like to use for functions, but f of x is pretty typical. So here's what we want to show. We want to show that f of x equal to 0 has a solution between x equals 1 and x equals 2. To do this, to be able to apply the intermediate value theorem, we have to at least observe that a couple things are true. Question 1, is my f of x continuous? For sure, because it's a what? It's a polynomial. Continuous everywhere, great. It's certainly continuous on the interval from 1 to 2. Some other functions you might encounter in other problems might not be continuous everywhere, but if they're being asked to use the intermediate value theorem, will probably be continuous on the interval that you're looking at. Or if they're not, then you won't be able to use the intermediate value theorem. Oh my God. Okay. So first note that f of x is continuous on the closed interval from 1 to 2. Even though we're asked to show that there's a solution between 1 and 2, not including the endpoints, it has to be continuous, including the endpoints. And then the second thing I'll point out is, well, to be able to equal 0, it has to go from below 0 to above 0, which is why we picked 0 to make it easier, because if you have to be below 0, you're going to be negative. If you be above 0, you're going to be positive. So typically what we do is we say, well, let's look at f evaluated at each endpoint. F of 1 is equal to 1 plus 1 plus 1 minus 10. which is 3 minus 10, which is negative 7, which is notably negative. And f of 2 is 2 cubed plus 2 squared plus 2 minus 10. I don't really care that that's equal to 4, let's see, 8, 12, 14, minus 10, 8, yeah, so 4. I just care that it's positive. Graphically, here's what's going on. F of 1 is negative 7. F of 2 is positive 4. And since the function is continuous, it has to go from here to here with no breaks. So somewhere between 1 and 2 had to have equaled 0. We don't have a choice. So we can conclude by the intermediate value theorem, since f of x is continuous and f of 1 is less than 0 and f of 2 is greater than 0, there must be a number C. Where does C have to live? Right, and I think it's important to say that between 1 and 2, such that f of C is equal to 0. Usually these problems require a fair amount of writing actual words. Yeah. Because it's a polynomial. So I know you just came in, but we did spend a good amount of time earlier today talking about what kinds of functions are continuous where. Yeah. You're welcome. Yeah. Let's look at one more example here. Yeah. Yeah. So I'll just remind you all that to be able to apply the intermediate value theorem, the function had to be continuous on the interval. And I'm not sure if it's your class or a different class. I saw one question about like this function being, I feel like it was a different class, but like a function being something that was discontinuous at one point and being asked like if you could use the intermediate value theorem here. And I was like, oh no, you can't because it's discontinuous. So, but I don't remember which class that was for. Yeah, what does it look like? Uh-huh. I'm curious what I was thinking about. That's exactly what I was thinking about. Yeah. So I'll just point out because I think so. Yeah, I think this one's kind of worth looking at here. I'll give this right back to you. The function was g of x equal to the square root of 12 minus x over 2 plus x. This is a perfect example of a function that is continuous on its domain. So even though it's not particularly nice, it's not a rational function, it's not a polynomial, but it certainly is continuous as long as it's defined. No, this is definitely the one I was thinking. Now there aren't other functions. So I'll just point out this function is continuous on its domain. You might have, no, I won't even say that. Don't even go there, James. But what I really want to point out is, so for example, and I'm going to pick some nicer numbers here. So I'm going to point out that, sure. Sorry, let's see. Let me pick some nicer numbers here. Yep. So on the interval from say, yeah, -4 to +3, we have that g of -4 is equal to the square root of 12 minus -4 over -4 plus 2, which is equal to the square root of 16 over -2, which is -2. And g of 3 is equal to the square root of 12 minus 3 over 2 plus 3, which is the square root of 9 over 5. So in a misleading way here, I could say, well, look, g of -4 is equal to -2, which is negative, and g of 3 is equal to 3/5 or 0.6, which is positive. So can we use the intermediate value theorem to show that this function has a solution when you set it equal to 0? And the answer is no, because that function isn't continuous on that interval. Specifically, where is that function undefined that's a problem for us? -2, right? -2 is certainly in between -4 and +3. So we can say, oh, g of x is not continuous at x equal to -2. So we can't use the intermediate value theorem to conclude anything. I will point out explicitly, this function doesn't have a solution equal to 0 between -4 and 3. The only place where this function would be equal to 0 would be if x was equal to 12. Because the square root of 12 minus 12 is the square root of 0, and 0 divided by 14 is still 0. Anywhere else, it's not going to equal 0. And then I think the question that asks something else about like showing it's equal to 1 somewhere. So I'm not going to do it, but I'll point out if I was trying to show that g of x equal to the square root of 12 minus x over 2 plus x was equal to 1, that's not what I would do. I would instead, I don't want to show that this is equal to 1. I want to show that this new function that I'm going to call f of x has a solution between whatever points I'm looking at. Now, for this one, you probably don't need to actually do that because they're giving you values. Like they're telling you something like g of, I don't even know what numbers they're picking here. G of 0 is equal to the square root of 12 over 2, which is some decimal that's like, I don't know what. Oh, it's probably like about 1.7. And g of, I don't know, something bigger. Like, well, in fact, let's say g of 12 is equal to 0. So if you go from 1.7 to 0 and you're continuous, which we are between 0 and 12, did you have to hit the value of 1? Yeah, you did. Because if you're going from a value of about 1.7 to over here a value of 0 exactly, and you're continuous between here and here, you got no choices. You had to have hit y equal to 1. That's the whole gist of the intermediate value theorem. Is if you start above a value and go to below a value and you were continuous, you had to hit that value. Or if you start below and go to right below above, either way. If you're on either side of the value and you're continuous between there and there, you have to get every value in between those y values. That's the whole gist. Yeah.
What if like they didn't include like -4 and 3? It was more like 0 to 3. Would that still apply?
Which would what still apply?
That it's discontinuous, so that's why we can't stop it.
Right, but I will point out this is not discontinuous between 0 and 3. It is continuous between 0 and 3.
So I could use.
Yes, certainly between 0 and 3 you could use. So the only intervals that you couldn't use the intermediate value theorem would be ones that included -2. Or I guess for bigger than 12, but bigger than 12 seems weird because it's just radically undefined, right? It's just like doesn't, right? In fact, what I would really recommend doing if it were me and I was like, I don't know what's going on here, I would graph it. So Desmos is a great tool you should all get used to using every once in a while. If you graph this thing, square root of 12 minus x, dividing by x, 2 plus x. Right, so you can certainly see that we have a vertical asymptote at x equal to -2. And then as you move to the right over here, the graph completely just stops at 12, right? It is no longer defined to the right of 12. And then you can also see that if you look at y equal to 1, oh yeah, well, you're definitely going to get 1 if x is between 0 and pick something bigger than whatever that is, right? 0 and 2, 0 and 4, whatever you like. Yes, you would. Yep. So you can look at this graph and see what the domain is. I'm getting everything from as negative as you want to be, right? It goes on and on forever and ever and ever in the negative direction. And then I'm missing -2, and I'm going everywhere from -2 to I have to stop at +12. So there's the domain there in words and on the graph. All right. You had a question over there? Okay. Okay. I know it feels like a lot in one day. What time is it? 11:15? Okay, cool. Yes.
Well, let's say that the variable is repeated. You bring the outside given, but it's not continuous.
So-
Two, so.
Right, so if your interval includes -2, then yes, we cannot use the intermediate value theorem because the intermediate value theorem requires continuity as one of the prerequisites to be able to use it. Yes. Well, so what happens if we plug in -2? Look at -2 here, I get the square root of 12 minus -2 over 2 plus -2. I get the square root of 14 divided by, not the problem, division by 0. And if you look back at the graph, we can see division by 0, or division, I should say, by a number that's really, really close to 0. So like if I were to start plugging in numbers that were really, really close to -2, like say -1.9 or -1.99 or 1.99999, the values are getting super big. So the problem here is that when you get really, really, really close to -2, the values either get infinitely large or negatively infinitely large. In other words, the function's undefined there. I should, I suppose, take a moment to say, how would you show this using limits? Well, oh my gosh, can you go away, please? So just to kind of revisit this for another second here. If we were to ask about the behavior around -2, we'd say, well, what's the limit as x approaches -2 from the right? And when you have a limit like this, again, what's the first thing you should do with a limit almost every time? Plug it in. So if we plug it in, we're going to get something unfortunate, the square root of 14, which is already unfortunate, over essentially 0. And now here's what we have to use a more critical eye. I didn't really plug in -2. I plugged in a number that's really, really close to -2, but a tiny bit bigger. So I want y'all to be careful and think about the answer to the next question. Give me a decimal number that's a little bit bigger, meaning to the right of -2. Yes.
-1.9.
Correct. Exactly. -1.9, right? Because we're a little bit to the right of -2, so we're a little less negative. So if we think about plugging in something like -1.9, well, 2 plus -1.9, is that a positive or a negative number? Right. So we're really dividing by a slightly positive number. And then when you divide a positive number, because square roots always spit out positive things, by another very, 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 very small positive number, you get a very, very big positive number. On the other side, if we approach -2 from the left of the same thing, you're still getting root 14 on top, but now we're plugging in a number a little bit more negative than -2, like -2.1. And then the denominator is going to be very slightly negative. So we have a positive number divided by a very, very small negative number, and we get a very, very large negative number, which exactly corresponds to the asymptotic behavior on either side. If you look at -2, if you look back at the graph I graphed, from the right side of -2, the graph is shooting up to positive infinity. On the left side of -2, the graph is shooting down to negative infinity. That's all I had to say there. You're welcome. No, it's good. It's good to explore that. Okay. Talking about slopes of secant and tangent lines and derivatives and all that good stuff. So I should point out, calculus really cares about limits. The whole, which we'll get to probably, yeah, you should get there. The definition of the derivative is the limit definition of the derivative. So every derivative that we do later on, where we don't use the long formal definition, is still based on this idea that you could write it as a limit definition. So I just want to really make it clear that all of differential calculus, like taking derivatives and stuff like that, is really based on the idea of limits doing what they do. So I just want to kind of remind you of that and encourage you to make sure that you practice your limit things and that you are comfortable knowing kind of what a limit's all about. Again, the limit's all about this idea of just as x gets really close to something, what is this expression also getting close to? Okay. So, where do you want to start here? Yeah, let's start with that. Let's start with the following example. I want to find the equation of the line tangent to f of x equal to, show us that way, x squared at the point, sure, -1, 1. And although the answer to this is going to be fine, we're going to do a little bit of exploring here. I'm going to draw a picture. I'll probably draw this picture a few times. And try this draw parabola a little bit more nicely than usual. Here's my usual parabola, center at the origin, or vertex at the origin. And my goal, when I should use my straight edge, it's good to have a straight edge, is to find the equation of this tangent line. Which, at least from my perspective, looks like it has a negative slope, but I don't know exactly what it is. And I can't just guess. So what I need to do here is, well, let's label this point here as well. So that's the point -1, 1. What we're going to do is, instead of right off the bat finding the equation of this tangent line, we're going to find the slopes of some secant lines. And we could do a whole bunch of different points, but really what we're going to do is we're going to take, and this is where I have my picture. Sure, fine. So I'm going to use a point up here. And let's call that point, do we want to call it A or do we want to call it X? I don't really care. Let's call it X. This point here is the point X comma X squared. Or A comma A squared, or you could actually pick a value and say it's like -3 comma 9. In fact, let's do that real quick. If it was actually the point -3 comma 9, so let's say that's up even further, say it's like up here, then there's the point -3 comma 9. Apologies for my not wonderful picture. And I want to find the slope of this secant line. A secant line just being a line that passes through 2 points of the graph. So great, I can find the slope of that blue secant line. It's going to be the difference in the y's, so 9 minus 1, over the difference in the x's, -3 minus -1. That's going to be 8 over -3 plus 1 is -2. That's -4. And the idea here, well, I say, no, let's do one more point. Let's say I also pick the point -2, 4. I use green, sure. So for -2, 4, I could draw the secant line again. Not as much fun. So, and the lines start to get really messy, which is why I try not to draw too many of them, but already it's looking like a hot mess over here. But for the green point, -2, 4, the slope of the secant line there is going to be, well, again, it's the difference in the y's, so 4 minus 1, over the difference in the x's, -3 minus -1. That's going to be 3 over -1, which is -3. So here's the gist. The gist is we're letting these points get closer and closer and closer to the point of tangency so that we can say that the slope of the secant line is going to get closer and closer to the slope of the actual tangent line. But the way we actually do that is to say, just pick a general point. Don't actually pick -3, 9 or -2, 4 or -5, 25, whatever. Pick x comma x squared. So we really want to know what's the slope of the secant line between any old point x comma x squared and the actual point of tangency, -1, 1. Well, again, it's still just your usual slope equation. The slope of this secant line is going to be the difference in the y values, so x squared minus 1, over the difference in the x values, x minus -1. And then we're going to simplify it. So I'll point out that x squared minus 1 over x minus -1, well, the numerator factors is x plus 1 times x minus 1. The denominator is x plus 1. And the x plus 1's cancel, and you get x minus 1. And I'll point out that if you plugged in -3 for x, you'd get -3 minus 1, which would give you a slope of -4. If you plugged in -2 for x, which I didn't write over here, which is kind of annoying, you would get a slope of -2 minus 1, which is -3, just like we did. So this is always giving us the slope of the secant line. So then here's how we find the slope of the tangent line. So the slope of the tangent line is going to equal the limit as x approaches 1 of the slope of the secant line. As x approaches -1, the point of tangency. So again, just the thing I said before, right? We're just letting this point get closer and closer and closer and closer and closer and closer to the point of tangency so that the secant lines actually tend towards having the same slope as the tangent line. So then the work here would be to say, oh, that's the limit as x approaches -1 of exactly x squared minus 1 over x plus 1. We do the algebra, right? Because typically, if you just plugged it in, you get a 0 over 0. That's why we spent time practicing 0 over 0 limits. It's because most of these things are going to be 0 over 0 limits. But then we do the factoring and canceling. You get the limit as x approaches -1 of x minus 1. Sorry about that. Looks terrible. And then you plug in -1 for x, and you get -1 minus 1, which is -2. And that's the slope of your tangent line at that point. AKA, that's the derivative of the function at that point. I know we haven't really talked about derivatives yet, but that's where all this is leading to, is that the slope of the tangent line at a point is one way of finding the derivative, or one way of interpreting the derivative. It's not the only interpretation, so I don't want you to just think, oh, derivative is always slope of the tangent line. That's one way to think about it, but a more general thing to say is a derivative is a rate of change. Here, it's how y is changing as x is changing. Right, that's what the slope really means. If your slope is -2, it means that for every 1 over x goes, you go 2 down for y. So you're saying, oh, y is decreasing by 2 for every 1 that x is increasing. Or the rate of change of y with respect to x is -2. And then we should answer the final question, which was to find the equation of the tangent line, right? Finding the slope is not enough, although the slope is really the important part. But the equation here, which I do not have enough room to squeeze in without making it look terrible. So if my slope of my tangent line is -2, and the point of tangency is -1, 1, then we can certainly use the point slope form to find the equation of the tangent line. It's going to be y minus the y coordinate equal to the slope times x minus the x coordinates. And most of the time you will be asked to isolate y and write this in the point slope form instead of the slope intercept, or instead of the, oh my gosh, be asked to write it in the slope intercept form instead of the point slope form. This is point slope. I want slope intercepts. So solve for y. Y minus 1 equals -2 times x plus 1. So y is going to equal -2x minus 2, and then we're going to add on the 1. That's going to be a y equal to -2x minus 1. Which seems reasonable, right? It certainly looks like the slope here, or sorry, the y-intercept here looks like it could be -1. So it seems like that's the right equation for my tangent line. Yes.
X squared minus 1 divided by x plus 1.
Sure. So, and let me actually just draw the picture again because I think it's worthwhile. So what I did was I said, for this point here, -1, 1, and for some generic point up here, x comma x squared, I want to find the slope, and again, I've drawn this terribly here. I want to find the slope of that line. Well, to find the slope of a line, where we know 2 points on the line, we just use the slope equation, which is the difference in the y's divided by the difference in the x's. So here, the slope of that secant line is the difference in the y's over the difference in the x's, or y2 minus y1 over x2 minus x1, which in this particular case is x squared minus 1 over x minus -1. Or if you prefer, you can totally switch the order and say it's 1 minus x squared over -1 minus x. Either way is totally valid. I'm usually trying to write it in a way where the variable thing comes first and the not variable thing comes second, just because it's easier usually.
Like, we're given at 1 point.
You have to make one up. The thing is, you always are given a second point. It's the point where your first coordinate is x and your second coordinate is your function, f of x. That second point always exists for all of us. It's just x comma whatever the function is. So let's look at another example to see how this is going to work. So, yeah, let's do that one. Sure. So let's say we want to find, do I want to do this the hard way? Yeah, let's do this the hard way. So we want to find the equation of the line tangent to f of x equal to the square root of x at x equal to 4. Again, I'm going to draw a picture. You don't have to draw a picture here. I just think it's nice the first few times to kind of get an idea to grasp what's really going on. Here's my usual square root kind of thing. And let's say, and I've not drawn this very well, such as life. Sometimes your pictures aren't perfect. So there's my point 4 comma 2. And I'm trying to find the equation of the tangent line, which again, I don't really need to draw here, but there it is. So I really want to find the equation of the tangent line, which means I really need to find the slope of that tangent line. Because once I find the slope, I'll have a slope. I already have a point, and I can use the point slope form to find the equation of the tangent line. So my real question here is, what is this slope? Just like last time, we're going to find the slope of a secant line and then take a limit to find the slope of the tangent line. So pick any other point. And again, I don't want to pick an actual point. I don't want to pick 9 comma 3 or 16 comma 4 or 10 comma root 10. I want to pick x comma what? What does the y coordinate have to be if the x coordinate is just x? Radical x. Whatever x is, the y coordinate is the square root of that because that's the function that we've graphed. So then there's my secant line that I'm going to find the slope of. Whoops. That looks terrible. Oh my God. The worst thing I've ever drawn. Sorry about that. It's no. So I'm shamed. That's the problem with having a short ruler like this is you go off the end. So let's find the slope between these 2 points. So the slope of my secant line is the difference in the y's or the difference in the x's. You can do this either way. You can do it as 2 minus root x over 4 minus x, but I would much rather do it as root x minus 2 over x minus 4. I'm going to simplify this, but I might as well just start writing the limit. So I want to find the slope of the tangent line. It's going to be the limit as x approaches what? Of root x minus 2 over x minus 4. And I'm sure you all can see that I have a problem. If I plug in 4, what do I get? Say the whole thing. 0 over 0, right? 0 over 0 and 0 are 2 very different things. 0 is a nice integer number that's beautiful. 0 over 0 is an indeterminate form that requires more work. So what am I going to do here? Well, there's actually 2 things I can do here. Right, that's the more typical thing to do, is multiply by the conjugate. And although I wrote this in red, I really don't like writing in red typically. So limit is x approaches 4 of root x minus 2 over x minus 4 times the conjugate root x plus 2 over root x plus 2. We multiply it out, we get the limit as x approaches 4 of x minus 4 over x minus 4 times root x plus 2. The x minus 4's cancel. You get the limit as x approaches 4 of 1 over root x plus 2. You plug in the 4, you get 1 over root 4 plus 2, which is going to be 1/4. And that's the slope of our tangent line. I will point out another way you could have done this, which is a little less obvious, but it is true that x minus 4 can be factored as root x minus 2 times root x plus 2. That would also work just fine. You get the same thing. But it's less obvious, I think. So then we've got the slope. We've got half a point. We can find the equation. So my slope is 1/4. My point is, well, the x coordinate is 4. And what's the, oh, no, we have the whole point there, sorry. So often though, you'll only be given the x value, and then you have to plug the x value into the original function to find the corresponding y value. So you plug in 4 into the function, square root of 4 is 2.
Plus minus.
Definitely not. Nope. Square root is only giving us positive values. If you're solving an equation like x squared equal to 9, then you get x equal to plus or minus the square root of 9. But the square root of 9 on its own is still just positive 3. Also, if you look at the square root function, which I've drawn here, what kind of y values does it have? Are they positive or negative? Right. So I want to make that extra clear to everybody. Square roots only ever give us positive outputs, not negative outputs. If you want the negative, you have to include a plus or minus because you're trying to solve an equation. So here we get y minus the y coordinate equal to the slope times x minus the x coordinate. We rewrite it as y minus 2 equal to 1/4 x minus 1. And then we add 2 to both sides to get y equal to 1/4 x plus 1. And that's the equation of our tangent line. All right, let's get a little, oh, question? No, you're distraction, cool. Let's get a little more general, because this is totally fine, except if I then went and asked, well, what's the equation of the tangent line when x equals 9, you have to do all this work again. And what I really want to do is be able to do this work once, and then answer the question for any particular value of x. So let's kind of look at, so yeah, we'll do that. We'll look at the same function. F of x equal to the square root of x. And what I really want to do is I want to be able to find the slope of the tangent line at, let me ask you all, has Adele done this using a comma f of a, or has he done it using x comma f of x, or has he done it at all? Like, has he written like an a here, like a comma f of a? And it's really okay if this, I'll just do it the way I think I should do it. Then we'll talk about it. Sometimes people use a's here. I'm going to use x's here because that's where we're eventually going to end up. Yes, we are. Great. So people use a first because first we think about the derivative as at one point, and then we move on to think about the derivative as a function. So that's the direction we're moving, is thinking about the derivative not as the slope of a tangent line at any one particular point, but the derivative as a function of the variable x. Cool. So what we're going to do is we're going to say that's x, that's f of x, and then just like the previous examples, to find the slope of the tangent line, again, because we want to know what's the slope of the tangent line, we're going to find the slope of the secant line. So we got to pick another point. So we're going to move a little bit to the right, or left, I guess, but we're going to go right, a distance of h. So this point over here, this x value is x plus h. And this corresponding y value is f of x plus h. So we're trying to find, or we're going to start by finding the slope of this line. And to no one's surprise, the slope equation hasn't changed. It's still the difference in the y's divided by the difference in the x's. So the slope of our secant line, oh, sorry, find the slope of the tangent line at x comma f of x, apologies. So the slope of our secant line is equal to the difference in the y's, apologies, f of x plus h minus f of x, all over the difference in the x's, which is x plus h minus x. People usually simplify the denominator because they can, and they usually just write this as f of x plus h minus f of x all over h, also known as the difference quotient. And then to find the slope of the tangent line, we're just going to take the limit as, everybody look, as this point gets closer and closer to that point. So that point gets closer to that point, what happens to the distance between x and x plus h? Right, it gets smaller and smaller and smaller. So in other words, to find the slope of the tangent line, we're going to take the limit as h goes to 0 of the slope of the secant line, or of the difference quotient. Again, with observation, I think you can all see if I just plugged in 0 for h right now, I'd have an indeterminate form. I'd have f of x minus f of x, which is 0, all divided by 0. And as we've seen so many times, 0 divided by 0 is always going to be an issue that we have to deal with typically algebraically. So let's actually do the work over here. We're going to find slope of the tangent line as the limit as h approaches 0 of f of x plus h. Well, a reminder, our function actually is the square root of x. So that's going to be the square root of x plus h minus f of x, which is the square root of x, all over h. And just like when we did this before, we're going to multiply by the conjugate. We're going to multiply the top and bottom by the square root of x plus h plus the square root of x, all over the square root of x plus h plus the square root of x. Multiply it out. You get the limit as h approaches 0. Again, I'll say this most of the time. When you multiply the conjugates together, you get the first thing squared minus the second thing squared. So we're going to get the square root of x plus h squared minus the square root of x squared. Which you should probably skip writing that and just write down x plus h minus x, but trying to be exhaustive here. On the bottom, you don't multiply it out. You get h times all that stuff over there. Oh, I should have said something before this. I mean, it's not like super important. I didn't say it already. But I should point out that whenever you're doing this, once you've written down this limit here of the secant line of the difference quotient, your goal is to make that h in the denominator cancel out. You want it to go away because you want to not be divided by 0. Because we're letting this point get closer and closer to that point, right? So if that point gets closer, what's happening to the distance h between x and x plus h? Right, it's getting smaller, smaller, smaller. So that's really why we're doing it. So, oh yeah, we're just letting this point move in towards this other point. We're like, oh yeah, the distance between them, which we've called h, is getting smaller, smaller. There is another way of doing this algebraically, which is worse. This is the nicer way to do it. The other way is usually more complicated algebraically. So simplifying this, we get the, sorry. So I was saying, you always are trying to make this original h in the denominator cancel out. Every other h can stay just fine, but the original h that's in the denominator has to go away. And to make that happen, we usually, before that, need everything in the numerator that doesn't have an h in it to cancel out, so that you have only h's or things with h's left in the numerator, which you can then factor an h out of to cancel the h in the denominator. So that's what we're usually looking for. So continuing on here, we get the limit as h goes to 0 of x plus h minus x all over the same denominator, h times the square root of x plus h plus the square root of x. The x's do subtract to 0. X minus x is 0. And then the remaining h divided by that h is going to be 1. So you have the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now that we've eliminated the original h that was in the denominator, we can substitute in 0 for the rest of the h's, or we can take the limit as h goes to 0 and get 1 over the square root of x plus 0, which is just the square root of x, plus another square root of x, or simplified 1 over 2 root x. Or written another way, 1/2 x to the negative 1/2. Another equally valid way of writing it. I point that out because when we start talking about the power rule, you'll see this version often more than that version. So then we can go back and answer the question, what's the slope of the tangent line when x equals 4? And if you plug in 4, you get 1/2 times 2, which is 1/4, just like we did in our previous work. But then you could also pick a different point and just not have to do all that work again. If I want to say what's the slope of the tangent line when x equals 9, it'd be 1/2 times 3, or 1/6. So that's the advantage of doing it generically like this, where you say, oh yeah, I can find the slope of any tangent line. I can find the derivative of this function at any point. And I still have a few minutes left here. So that's what I should really kind of end with here is that, sorry, I'm going to not try to cover up everything here. So definition, the limit definition of the derivative says that f prime of x, which is the derivative of f, I'll write that down in a second, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And I'll point out that this here, this is notation for the derivative of f of x. That's not the only notation for the derivative, but it is a common one that we use all the time. You should definitely memorize this definition. Specifically, that the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Question?
The 68, 72, and 75
Mm-hmm.
on there. I don't know if you could like kind of explain that and see if like it's.
What are those problems? I have no idea what they are. Okay, and specifically asking like what kind of thing?
Yeah, asks for if there's two, find the equations of both lines to the points 2, -3 that are tangent to the parallel.
Sure. So you're trying to find you got this parabola, and you're trying to find the equations of the lines or the points of tangency, or
Equations of both lines through the point.
so I'll point out that there's some point up here, probably kind of high, where the tangent line would go through that point over there. And there's some other point over here where the same thing would happen, maybe like right about there. So we're trying, so really to find the equation of either one of these lines, you have to find the point of tangency there, right? So how are we going to do that? Well, I'm going to call this point a comma f of a, which in this case is going to be a comma a squared. So here's the general gist. So what's one way I could find the slope between the point a comma a squared and the point 2, -3? Well, just using the slope formula. So the slope would equal the difference in the y's, a squared minus -3, over the difference in the x's, which is a minus 2. Great. What's another way we could find the slope at that point?
Derivative.
Right. So the other way using the derivative is going to see, well, we only have the limit definition of the derivative at this point. So we say, okay, well, if I want to find the derivative there, my derivative is going to equal, and I'm kind of run out of room here. I brought it right over here, actually, sorry. Apologies. So I could say that f prime of a is going to be the limit as h goes to 0 of f of a plus h minus f of a all over h, which is going to be the limit as h approaches 0. F of a plus h is going to be a plus h squared minus f of a is a squared all over h. We multiply that out. The limit as h goes to 0 of a squared plus 2ah plus h squared minus a squared all over h. You cancel the not h things like I was saying before. So now every remaining term in the numerator has what? Has an h. Great, we can factor out an h. So we have the limit as h goes to 0 of h times 2a plus h to the first, all over h. The h in the denominator gets to cancel out. And then we have the limit as h goes to 0 of 2a plus h, which is equal to 2a plus 0. And that's another way of writing the slope of this line. So now we have this slope, which is the slope of this tangent line, and this slope, which is the slope of the line here, should be the same. So now the way we figure this out is by setting those two things equal to each other. So we're going to set a squared minus 3 over a minus 2 equal to 2a. Your job then is to solve for a. You should get two different solutions. One is going to give you, you should probably get one that's positive and one that's negative. And then those will be the 2 points of tangency, and then you can find the two equations of the line by finding the equation of that line and the equation of that line. That's the general idea there. It's a little bit much, but it's not too much. And I would definitely solve this by multiplying both sides by a minus 2.